Hello, my name is Steven. Welcome to HiFinder Tech Talks, where we focus on understanding the technology and engineering that makes the hydrogen economy work. I'm very happy today because we have a special guest who is an expert in mechanical engineering and innovations, and he even went on to found his own company to make inverters. He is connected to us live from his lab, actually, and I'm very happy to welcome Jean Duredier of ePower Labs. Hi, John.
Hi, Steven. Good morning. So thank you for the introduction and for inviting us to your Tech Talk in the HiFinder community. So it's a pleasure for us to explain here, let's say, the technology that we are providing for the hydrogen community as well.
Perfect. Thank you, John. So the good thing is that not only can I talk to you, but you also have some equipment all around you there, and you have some. I see you have something on the table. Can you show us that? Yeah, is that one of your inverters?
Correct.
Can you tell us what that is?
Correct. So as you previously said, so we are currently in our test laboratories, in our test cell. So this is where magic happens, where we develop this kind of products. And today what we brought is a traction inverter. So this is an inverter that we have developed that we are providing currently to our customers. And this is particularly a 400 volt inverter for this kind of architectures with a power of 150 kilowatts nominal power. And this is currently what we are really selling, let's say, to our customers who are developing both electric with batteries and hydrogen vehicles. So this is the product that we are bringing, let's say, as well to the hydrogen economy.
Okay, perfect. So now you mentioned it's an inverter. It's a traction inverter. Okay, I know that there are, you hear the word inverter all the time. There are several inverters. So can you tell us exactly where we can find this one, in the whole setup, please?
Yes, I assume that you were making these questions, so I prepared some slides just to make an explanation where we can find this kind of inverters. Because as you said before, so there are several inverters in a fuel cell powertrain.
Yeah, we see them here.
Not all inverters are the same. So as I'm sharing the slide, so you can see a schematic from a fuel cell powertrain. And in the front of the truck, in this case, it's a heavy-duty powertrain, you can see the fuel cell itself. And then following the orange lines and the cables, so you see in the middle is like a battery shape, and then we have at the rear two modules here, which are traction inverters, and the two traction models that we have here. So I was making this clarification, let's say, because here as well in the fuel cell, we have some compressors, some recirculation pumps that, depending on the architecture of the fuel cell system itself, they are having one or two inverters to control these devices. And those devices, those applications are running at higher speed, and they have different requirements. So the inverter is different. So they consume less power, but they have other challenges. But today, so we are talking about the traction inverters, which are these two components here in this powertrain setup. And this is exactly what we are developing, what we are on the table today, and what we are as well validating in the test cell and supporting our customers to bring them to the market.
Okay, so that means the inverter is essentially what is between your power source, your fuel cell system, battery, whatever it is, and the motor. So can you tell us exactly what the inverter does? I mean, to just maybe shed some light. Does it turn the current around, or what does it actually do?
Yeah, so the electric motor controller, how is properly properly said, it's a device that controls AC motors, for instance, and they get the power in a vehicle. They get the power from the battery or from the fuel cell in this case. So the fuel cell and the battery, they generate what is called a DC bus, which is a voltage, let's say, in a continuous voltage from the system. And then those devices are, let's say, translators of the power, and they translate this DC current into the AC current just to command the motor.
Okay.
And to do that, because it's not, let's say, an easy challenge, well, as I said before, here we have on the left side the DC supply, so the DC power source, which is generated by the battery and the fuel cell itself. And on the right side, we have the electric motors. And the electric motors, the three-phase electric motors, so they have 3 phases, and the currents are shifted, let's say, by 120 degrees. So then from this side, we have to translate the current to, let's say, to control the machine properly.
Mm-hmm.
And this is why we have in the middle an inverter. So this is the basic schematics from an inverter. On the left side, we have the DC supply. Then we have one capacitor here in the middle. And then we have the power stage or the power module. And at the end, we have here the motor that is exactly what we want to control. So then the question is how we make that, right? So how can we translate a constant current, let's say, to a AC current? So for this, let's say, challenge, so this is why we have these switches. The 3 upper ones are the high side and the low side. And then what we do essentially is following. So we need to emulate or to generate, better said, sinus waveform.
Yes.
So to control, as you saw before in the graphs, we need 3 sine waveforms. And for that, we switch between the high side and the low side to generate this waveform, let's say, swiftly. And of course, we need to do that, but the inverter itself needs as well some inputs. So you can't just generate some signals without any currents, because we have to be aware that this inverter goes somewhere in a powertrain and someone else has to tell the inverter how much power we want, how much torque we need, and so on, either to move the vehicle or to move whatever pump that we want to drive. And for that, it's always required to have, let's say, in a higher level, like driver demand, which is called in a vehicle level, where all the inputs from the driver, like accelerator pedal, brake pedal, steering, ABS, ESP, whatever, all this information is gathered to a vehicle control unit. Among this information, normally like powertrain monitoring and other kind of watchdogs are as well included. And then from that level, a torque set point or speed set point is sent to the inverter, and the inverter translates this set point into, well, let's say, follow down the river.
Yeah.
It translates into a PWM signal that generates this wave and then starts moving the motor. Then the feedback from the motor goes back to the inverter and then goes back to the driver to say, okay, you are requesting 50 Newton meter, you are getting back 49, for example.
Okay, so that means it does
how
this
the loop is closed.
Yeah, okay. And so obviously the acceleration, but the braking as well? So does the braking happen as well through that?
Correct. So we can, with the electric motor, we can generate torque or positive or negative torque. So with the positive torque, when we are driving, we are, let's say, accelerating the vehicle, making positive torque. And when generating negative torque, we are recuperating energy. So then we are getting energy back from the road, so from the wheels to the transmission to the motor to the electric to the inverter, sorry, and this goes back to the battery, and then we can recuperate some energy and
so
use
the inverter does both. It does both of them. It's happy to do both. Yeah. Okay.
Correct. Exactly. Yes.
Okay. So up to 140 kilowatt. That's the unit that you just showed us now.
150.
150. Yeah. Okay. So
size matters.
Yes. Okay. So now I see you there in the lab, and I mean we've seen this. And tell me, in your lab now, where do you actually fit this to test this now? So tell us through that. Can you take us through that a little bit?
I brought you to this location because I think it's a good place to show to the audience, to the people, what is required, let's say, when you are testing an inverter. So just imagining or saying this inverter has been already validated, all the parts, all the software and so on, it's already free. So it's working. So then when anybody is trying or is willing, let's say, to build up a powertrain, so there is always a question. It's like, what motor do I need for my application?
Yeah.
And then when people start searching for a motor, then they say, okay, I need one inverter to control this motor. Then what we do is we assess our customers. So we assess them on selecting the motor, for example. So seeing if the speed and torque is matching, let's say, to the vehicle requirements. Once we find a motor, then of course we have to see that it's matching to our inverter specifications. And if physically both systems or both components, better said, are, let's say, matching together, then we need to pair them. So we need to calibrate them. So we need to calibrate the inverter for this specific motor. So in that sense, we work with different motor suppliers, and there are two options. So the motor suppliers, they provide you with information. So with the PAC-EMF information, short circuit test, with all IDIQ tables, whatever information we need. And if so, then we can already parameterize the inverter, let's say, upfront, and then let's say offline parameterization, and then we can go to the test bench to make the final test and validation and so on. Or we do the second way is to take the motor, we go to a test bench, and then we do the entire characterization. So we run PAC-EMF testing, short circuit testing. We do the MTPA. MTPA is the test procedure that we use, let's say, to find the optimum point, the optimum IDIQ point, set point for a specific operation point. So just summarizing, there are different configurations to get for a given voltage and temperature a desired torque. For example, if we are searching 50 Newton meter torque, then it's possible to get it with different IDIQ configurations, but there will be an optimum one which gives you the best performance and the highest efficiency. And this is exactly with this MTPA what we are doing. For the entire operation map, we try to get the highest efficiency point and to have a good transition smoothness of the system that laterly the end user will have in the vehicle.
Okay, so that means in this setup that you have there, that's where you do the calibration. And what is what? Can you tell us the blue element on the bottom? Can you tell us what we're seeing there, please?
So I will try to point. I think it's somewhere here.
Yes, so, correct.
This one, this blue motor is the dyno, so it's the brake dyno. Mm-hmm. This one generates the brake torque that it's, let's say, braking the unit under test that we call, which is the motor that we want to calibrate. So following this line in the middle would have a shaft with a torque sensor. Let's say with a device, we measure the torque on the shaft, so the torque that is generating the motor. If we follow a bit further, you will see that there is empty space.
Yes, there's a hole
right now there an empty space. Mm-hmm. Yes, it's a hole. It's the place where the test motor is supposed to be.
Right now we're making there is no motor there at the moment there.
Yeah. Correct. Mm-hmm. Right now we're making a test bench setup change because we are starting a test campaign for the next 20 weeks, and then you were lucky and you could find this this slot here in test bench. And then following the line, let's say we have exactly here. So this device there, this is a power analyzer. So this device measures the current in the DC side, so before the inverter, so current voltage before the inverter, measures current voltage after the inverter, so in the AC side, and measures as well the torque after the motor. And with this measurement chain, we can measure the efficiency from each component and from the entire subsystem, let's say in high speed. So we are making measurements up to 2 megasamples per second, which is very, very fast sampling, let's say. And with this information, we are able to make a very accurate and precise calibration for the inverter.
Okay, and so for that setup, that's what you need. And the things at the back, those are your power supply and so on, I would imagine.
Yeah, so we have following the orange cables here. So we are going to the backstage where we have 250 kilowatt battery emulator that it's used just for this test cell. So there are other modes as well. And we have additional equipment, which are the coolers. So we have as well a climatic chamber. We have automation system, which is very, very important to have a robust automation system that gathers all the information together from external sensor, from CAN communication, from all the equipment. Because once you have a proper automation system, let's say, it helps a lot making a short post-processing activity and having results in a fast and quick way. And of course, having results means that you need to have trustworthy results. That it's key of the testing.
Okay. Wow, super interesting. What you need to make that all, that one component work. Let's just zoom back into that one. So this one now, it's. I mean, I always thought that they were bigger. To be honest, it seems to be looking smaller. Can you maybe give us some insights on what's about this one? Yeah.
So as you mentioned at the beginning, so I found this company together with my colleagues. We were working in the automotive industry. Not myself, but my colleagues, they were designing this kind of power electronics for large automotive industry. And our ambition is to bring, let's say, the state of the art in performance, including weight and performance, to this kind of low volumes markets, so which are not large automotive. And in that sense, we have in this package of 5 kilograms, so we have 150 kilowatt of power, which right now it's a very competitive power to weight ratio. And I would say that, well, with this technology, which is IGBT, which is a standard technology that it's really very well known and very spread and common, towards the entire industry. This is a number to get that we are very proud of. So it's not so easy to achieve this kind of compact design that, well, it's at the end, if you have a compact design, it makes the life easier to the vehicle integrated to integrate it, because nobody wants an inverter. The vehicle integrator wants to sell the vehicle, yes, and he needs an inverter to sell the vehicle. This is the truth. So we try to make the life easier. We make it small, compact. We have several configurations to make the integration. For example, this is a water-cooled inverter. So here we have frontal cooling, but in case that the integration requires another cooling, so we can have, let's say, longitudinal cooling. So the cooling pipe will come in this side and then would exit in that way. Or we can have the frontal one, as I said. And then this gives a lot of flexibility, let's say, to freedom to the integrator to
what kind of temperatures? What kind of temperatures does your cooling system work at? So I was asking, what kind of temperatures does the cooling system require?
Yes, so let's say nominal cooling flow, it's 8 liter per minute, let's say, and the maximum temperatures that, well, I would say 60 degrees Celsius is something that it's, let's say, operating temperature in conditions that we are already testing with customers.
Yeah. Okay. Cool. Yeah. No, that
can go higher, but normally it's something like this. It's stable.
Yeah. I was asking also, because that's also important for the integration aspect into the entire vehicle. You don't want to build a separate cooling just for that. Okay. So, obviously, I like the way you said no one wants an inverter, really. I mean, clearly, we are talking about, getting the engine going. Any other, let me say, particular points about this product that are worth mentioning?
Yes, I would say, I don't know. I would say we designed this device, let's say, or this product, with all the lessons learned that we took from the automotive industry, and we are bringing all these kind of trips, let's say, to the market. And in that sense, for example, we develop a new system, which is we call, let's say, a quick release system to integrate the cable or to mount it. And normally, when you are putting a cable inside, you don't know how far you have introduced the cable and so on. And if you reduce the contact surface between the cable lag and the capacitor or the AC phase itself, then you generate a hotspot. So just to make a robust connection, so we design a system where you take a cable, so you just introduce it like this. Give me 1 second. Cable is twisted.
No worries.
Like this. Yeah. So then you get a mechanical feedback, and it doesn't come back.
Okay.
So this is something that when you are in the vehicle and then you have to make some changes or whatever, this is quite user friendly. Let's say this kind of systems. This is something unique that we are patenting right now. And then we support, let's say, with the entire processing. So from the test bench, so it's a turnkey solution. So we support the customer with the entire calibration. We assist them as well on the vehicle. So we provide as well tools. We have our own tools so to make calibration, to make diagnostics and so on. And then right now we are as well testing with our customer, with our first customer, one new setup, which is we are connecting our inverter, let's say, to the cloud. And then we are capable of making remote monitoring, remote diagnostics, and everything from all locations. So the customer doesn't have to take care about the inverter, and if it happens, we can monitor everything from remote, and all this information can be as well be useful for the fleet operator to understand, let's say, or to have more information from the inverter or from the powertrain point of view on how the fleet is being operated, or to get more information that is useful for them.
Yeah. Wow. Okay. Who would have thought that we come from inverters to a cloud system that is now integrated in fleet management? John, I must really say I've learned a lot now. I would have not thought, that my inverter sitting in the vehicle is the one connected to the cloud and getting all the vehicle data. Unfortunately, we've come to the much time that we have. Thank you very much for showing us so much about this.
We could spend more time, but well, next time.
Don't worry. The way things are going, I think that you will have much more to share with us very soon. All in all, I want to say thank you very much for showing us that. And to the audience, thank you very much for watching. This has been the Highfinder Tech Talk with Jean Durodier, connected directly from Spain. Beautiful country where also we get high tech for the hydrogen economy. If you want to find out more about them, please go to highfinder.com, and then you can find the products there, and then you can get into contact with John and his colleagues who will help you with all the things that you need to know around that. If you like this video, please drop a comment or subscribe, or maybe say something on LinkedIn or wherever. We'll be happy about that. And also we'll be happy if you come back to watch another video, which will make some time. Thank you very much. And thank you, John. Have a wonderful day further.
Thank you, Steven.
Bye.
Thank you. Bye-bye.